Okay, so were there any questions on the material we covered from last time? All right, if not, so today what we're going to do is we're going to review a little bit of what we covered last time and then move forward to look at estimating the HRF. We're also going to start introducing sort of a geometric picture that is sometimes useful for understanding what all these statistics are doing. And then we're going to really get into, spend the bulk of the lecture talking about nuisance regressors. Okay, everything that's sort of not the signal and how we deal with that. We'll also talk a little bit about what happens when you have correlated regressors. And we'll end with experimental design and efficiency. So we're not going to get through all the slides that are posted, but probably the last part I'll just sort of zoom through just to give you a sense of design and efficiency. Okay, so from last time we spent most of the lecture talking about the general linear model, which is shown here. In this we have two stimulus each, and after we convolve it with the HRF, we get our regressor for stimulus 1 and the regressor for stimulus 2. We basically enter those regressors into our general linear model, so those form the columns of our design matrix. And then our goal is to estimate beta 1 and beta 2, and then also to form test statistics based on those estimates. So this is an example of what a beta map looks like. So it's these beta maps that we're actually going to then send up to the group analysis. Okay? So just to remind you, there are two main test statistics we talked about. There's a T statistic and the F statistic, and they're both based on this general linear model. So far for the general linear model, we're not really considering nuisance regressors yet. We're just assuming that we have the stimulus, and that's all we care about for now. So for the t-test, you can have either a one-sided test or a two-sided test. Okay, you can test whether your contrast C beta is greater than 0 or whether it's just not equal to 0. Okay, so which test you do determines your p-value and your thresholds. So typically the two-sided test requires a higher t statistic to pass any given alpha threshold. Okay, so the t-stat, and then here we've written the t, and this is the number of degrees of freedom. So once again, n is the number of rows in your design matrix, and k is the number of columns. Okay. So that has the form of, we have the contrast on the top, and we have the square root of the variance, or essentially the standard deviation of that contrast on the bottom. Right, so that's always the form of t-statistic. It's always sort of what you care about divided by its standard deviation. And then if we write it out in terms of the general linear model, the top stays the same, and let's unpack the bottom a bit. Bottom, the denominator has two terms. One is this sigma hat. So sigma hat is just your sample standard deviation. Okay, that's basically computed from your residual. So everything the model can explain is your error, and the standard deviation of that error is your sigma hat. Okay, so that tells you basically how noisy things are. So if that sigma hat is really large, that means you have really big residuals, and so probably you didn't have a very good model fit. Okay, but just knowing what the sigma hat is alone doesn't really tell you much, because you really have to compare it versus the size of your contrast. So C beta hat is large compared to sigma hat, then in general your t statistic is going to be pretty good. Okay. There's another element, which is essentially this term here, which the only part that really depends on the design is this x transpose x inverse of that. So let's unpack that a little bit. This x transpose x tends to increase with the number of measurements you have. Okay, so the more measurements you have, that term gets bigger and bigger and bigger. Okay, and so since we're taking the inverse of that, actually, basically this, it's going to make this term get smaller, and so it's basically going to make the t statistic bigger. Okay, so the more measurements you have, your t statistic will tend to go up. Okay, and also the corresponding p-value will tend to go down. All right. So that's just basically saying that the more measurements you have, the more confidence you have in your parameter estimate. So even things are very noisy, if you just, so that's the whole idea behind averaging. Even if things are very noisy, if you measure for a very, very long time, you can average that noise and have a better idea of your parameter estimate. Okay, so that's why we're always talking about sample size. I'm not sure we'll talk too much about power in this course, but in terms of, we're always talking about what's the minimum sample size required to achieve desired power for your study. Okay, and so that's part of the reasoning why we need more subjects, because having more subjects helps increase that statistic. Okay. And the last thing about the t-stat is the contrast is specified as a vector. Okay, we're just specifying one contrast for the t-statistic. So when you do, for example, AFNI, you can specify many, many t-statistics, and for each one you will get, for each contrast that you specify, you will get a t-statistic out. All right? So that should be a review for most of us, but any questions? Okay. So on the other hand, the FSAT is going to be for two-sided tests. It's inherently a two-sided test because the F statistic is always positive. Okay. And it has this form, which is a little more complicated than the t-statistic form, but you can still see it still has this sample. Now we have the sample variance, okay, because everything is squared for the F statistic. We still have our parameter estimates, but you see that coming in twice. Essentially, we're going to take our parameter estimate and square it, and then this term here has still got that x transpose x. So this term also, the more measurements we have, this term will get larger as well. So it has a very similar properties to the t-statistic, but it's just essentially, you can think of it as the square of the t-statistic. Okay. So where is the F statistic useful? Well, it's basically where you want to say, you want to look at multiple contrasts simultaneously, and you want to say, did anything happen, essentially? Okay. So like, I don't really care which contrast happened. I just want to see overall, was there either one contrast that was really large, or maybe all the contrast were sort of medium. And so the F statistic is going to be different from the t-stat in the sense that you're going to have, in general, a matrix. Okay. And each row is going to be your contrast. So that's the main thing, main difference. Now, obviously, you could just have one row, in which case the t-statistic and the F statistic are basically doing the same thing. Okay. But in general, you're going to have multiple rows for your F-stat because you're just looking for an overall effect. All right. And this R thing is the number of, it's strictly speaking, it's the rank of your matrix, but for all practical purposes, it's typically equal to the number of rows. Okay, so for this course, we'll just assume it's the number of rows. Okay, any questions before we move on? So, and just as I mentioned, if we just have one row, so that first number, that first degree of freedom is equal to R. So if R equals 1, then the F statistic can be written in this form, and it's just the square of the t statistic. Okay, so that's nice. So essentially, you can think of sort of, they're both signal to noise ratio. It's just the t-stat is sort of your parameter estimate over its standard deviation, and then the f-stat is sort of like the parameter estimate squared divided by its variance. All right. Okay, so I'm going to introduce a geometric view, even though it's not, it's used not so much in FMRI, although, there are papers on it that we've published in FMRI, but it's also, it's just sort of a nice way of sort of thinking of how these different statistics are related, because, through the course of your learning, you probably learned about t-stats, you probably learned about f-stats, and also you've learned probably about correlation coefficients and something related called coefficient of determination. So the idea is, typically these are derived with lots of algebra, but it turns out that they're all related. And so it's useful to sort of have that knowledge that all these statistics are actually all talking about the same thing. It's just a different way of looking at it. So I'm just going to spend a few minutes giving you sort of a flavor of what it looks like. And so we're going to assume that the contrast matrix for the F-stat is just what's called the identity matrix. So it just has ones along the diagonal. Okay? So it's going to be basically looking for every effect. All right. So if the identity matrix, if the contrast matrix just has ones, then it's just going to, it's similar to this one here, where this was saying, if I have C beta hat, and that's just 0, 1 like that, then it just gives me beta 1 hat, beta 2 hat. Okay? So the test statistic is now just comparing whether beta 1 hat is equal to 0 and also beta 2 hat is equal to 0. Right? So I have the assumption, then the f-stat actually has this really nice form. Remember, this is sort of our data here. That's what we measure. This is what we can model. Okay? And this is the error. Okay? So the f-statistic has this form. It's basically the length of this thing. This is what you can model. Okay, this is the amount of the data that you can model, and you divide it by the error. Okay, so that's all the f-statistic is doing, is saying how much of the data can I explain? I'm going to square that. How much of the data can I not explain? And it's the ratio of those two squared. That's the f-statistic. And then you adjust for the degrees of freedom. Okay, so it's related. If we call this theta, it's basically the cotangent square root of theta. Okay. So when you're looking at f-stats, this picture is useful to keep in mind because you're always looking at how much of my data can be explained by my model, divide by how much of the data can't be explained by my model. That's the f-stat. And the t-stat has a similar interpretation. So then what's the correlation coefficient? Okay, because you also hear about that, and often on FMRI, when FMRI first started, it was all talking about correlation coefficient. And still people, when you're doing, for example, resting state FMRI, you will often talk about the correlation coefficient. So then the question is, well, why do we talk about correlation coefficient? Why don't we talk about t-stat anymore? Okay. It turns out that they're related. So the coefficient of determination, which is sort of like the multidimensional extension of the correlation coefficient, is simply given by this equation here, which is now this length here. It's still the model, but now you're dividing by this term here, which is the data. Okay, so it's basically now it's asking the question: how close is the data, is the model related to my data? Okay, it's the ratio of those two, which is basically the cosine square root of theta. Okay, so it turns out the f and the r are related. So the r squared, for example, gives you sort of what percent variance of my data can be explained by my model. Okay, so if r squared equals 1, then those two vectors will be totally aligned, and so that means all the data can be explained by model. If, for example, my data was like this and my model was like that, then none of my data can be explained by my model. In this case, r squared would equal to 0. Okay? And also f would equal 0 as well. Okay? Because in that case, the data is here. What I can explain is nothing. I can't explain anything. Okay? Because this is my model space. All right. So we'll come back to this picture because this picture is going to be useful for us when we look at nuisance regressors and how correlated regressors and nuisance regressors can affect your interpretation of your data. Okay, so before we move on, are there any questions on that? Okay, so we're going to look at estimating the shape of the HRF. And so this is what's called a periodic event-related design. We'll talk a little bit more about designs in the second half of this course, this lecture. But for now, just assume that there's a stimulus at every point here. Okay. So I'm just banging. For example, I'm flashing a light every 30 seconds. And in response, I get the hemodynamic response function. Okay. So in this case, if I wanted to estimate the shape of my response, it's pretty easy. I could just average all those responses, and I could come up with some estimate of my response. Okay. But that's really not very efficient because you're only presenting stimuli very infrequently. Okay. So, but still, if you really want to measure the response, you do it. So this is a study we did probably about 15 years ago now where we looked at the effect of caffeine. So this is your brain before caffeine and then this after caffeine. So changing the hemodynamic response. Okay. And that was done with that thing where we just, every 40 seconds, we showed some light. Okay. So where the field has gone, and this is now getting into what's called event-related FMRI, which we'll talk more about later, is saying, well, that's a really inefficient design. So instead, I'm just going to present stimuli randomly. Okay, and here then and this is what I'm going to measure. Okay, and from this, I want to come up with some estimate of my response. Okay, but you can see if you just look at that wiggly waveform, it's not really easy for a human being to sort of estimate what the response is, right? You're going to actually have to use some math to figure this out. But the idea is we want to come up with an estimate of the response, and the question is, how do we do that? So I'm just going to sort of map out how we might do that, and obviously the answer is we're going to use the general linear model. Okay. So our goal is to come up with some estimate like that, and this is, let's say this is our stimulus. Okay, so if our hemodynamic responses had 4 numbers, we know that this is sort of like, this is the response if I sort of flash the light at this point in time. So first there's a response here that comes right away. Then there's a response that's maybe delayed by 1 time point, and then another response delayed by 2 time points, and the response delayed by 4 time points, or 3 time points, okay? So each of those elements of my response is sort of a delayed response, okay? So what I can say is, I can say, well, my data then is going to be equal to my stimulus times the response from the first time point, and then the response to a delayed stimulus times the second time point, and then I can just delay my stimulus, okay? And sort of multiply those by those coefficients. And if I write that in matrix notation, I just end up with my stimulus shifted along as I move along the columns, it's just shifted by each row. Okay? So the main point of this is just to tell you that we can very easily model these response functions in that way, where whatever stimulus you have, the design matrix is just going to have shifted versions of that. So this is an example of that, which is here there's some stimulus. Okay, so this is the first, that's the stimulus. So if I look, it looks like it's this periodic design where I'm just hitting the brain with stimuli periodically. And then to do my design matrix, you see each column is just a shifted version of the previous one. Okay, so whenever you see a design matrix that looks like that, you know that probably the person is trying to estimate the shape of the response. Okay. In this case, it looks like, how many parameters are they estimating? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So they're estimating 12 betas there. Okay. The other thing is, notice that this design matrix has nothing to do with the shape of my response. So previously, in making our design matrices, we took our stimulus, we convolved it with the hemodynamic response function, we came up with our regressors. Now you can sort of see it just depends on the timing. Okay, and we'll get back to that later in this lecture. Okay, so let's open it up for an exercise. We're going to do this old school, so I'm going to have you get into groups of like 2 and 3, and then we're going to randomly pick a couple groups for some response. Okay, so you're going to spend the next few minutes talking about what would be some useful contrast vectors or matrices, assuming that this was a design matrix. And this is an example of the parameter estimate. So this is an example of the hemodynamic response function that you would measure if you did that, if you solved using this design matrix. So go ahead, get into little groups, talk about, and each come up with 1 or 2 or 3 options for what would be some interesting contrast vectors or matrices for this experiment. All right? So at least 3 groups will be picked. Okay.
I think so. So I mean, are we maybe like something? But I will
Oh wait, I think this is yes, this is I think that's the simulator, right? The light? Yeah. Okay. So this is where it's like the so like here, oh yeah, so yeah, yeah, each column is physics, right? So then you would have all across at a certain time. So I don't know. Or would it be like one and then the bottom? Yeah, he did yeah, or Monday. But I don't know if we can read out. Yeah, yeah, just one. Well, I mean, isn't that this? Yeah, it was just, I don't know. Well, okay, what is the no, oh, yeah. Oh, well, yeah. That's where you would expect that everything is a one. This is on purchase. Oh, it's like you think that's how long it's been on? That's one is so maybe like after too long then there's an situation. So like yeah, so this right, because then maybe like 6 is up. So from the board, yeah, so this is so then maybe the 6 and the point of it yeah. Is this people and yeah. Is this people yeah. Right. So then the measure is what time what's the other right? Yeah, so it's all flashes. So like the I don't think it's on if that is then it's on like 4 seconds. Then I think that makes sense. We're trying to figure out like what duration of showing this. Yeah, we're getting the best response. Yeah. Because after a time then you just so it's just it would just that part I that part. 12. Well then you could just if you're just trying to do one we do
Okay, let's see what people sort of came up with. So before, does any group want to volunteer an answer? Just get it over with. No free will? Okay. All right, how about, let's ask the group back in the corner, because it seemed like you converged to a solution.
I don't know about a good solution.
Okay, sure.
I mean, well, we were talking about like how you discussed the diagonal of ones, you know, to look at each like event independently. 12 betas.
Okay, so we could have a diagonal of 1s.
Right.
Right, so the dimensions of that would be 12 by 12, right? Okay. So that's certainly a good choice. So what would that tell you? What would that be testing?
It tests like there's a signal for each of the betas, just independent of the others.
Right. Okay. So it could be. It basically is telling you, is anything there? Was there a hematic response at all? So it could be one was really strong and everything else was small, or it could just be overall there was something there. Okay. Yeah. So that would be a good choice.
I have a question.
Yes.
So I understand why the columns would be 12 because it's for each of these
Mhm.
beta parameters.
Yeah.
Why would it be 12 rows?
Because because if there's 12 possible betas, if you want to check each of the betas, you need a row for each beta. Yeah, if you're taking one beta at a time, and there's 12 betas, you need one row. Yeah.
So you
Yeah.
would do an F for that?
Yes, you would do an F statistic for that. That's right. So this would be for your F statistic. Okay, with degrees of 12, and then however many data points you had, determine the other degrees. Okay, any other group want to chime in? Okay, let's pick someone from this side. How about your group back there? Any answer is fine.
Could be the sum of beta 1 or
Okay, so what would the contrast matrix look like? Tell me the elements.
just 1, 0, 0, 0. Just look at the first one.
Okay, right. So you can just look at the first one, right? So you say is the first element. Okay, so that's reasonable. Okay. How about you guys? What did you guys come up with?
We came up with the identity matrix.
Identity matrix. Okay. Did anyone come up with anything anything else? What did you guys come up with?
We thought like the T statistic, we could just look at like one row of contrast with like one negative one, and then we can give you zeros after that. To look
Okay,
at
so like the
just
first
beta
two.
one, beta
Yeah.
two, beta two. Yeah.
Okay. Great. How about you guys? What did you guys come up with?
We thought about doing maybe a contrast between like the highest and the lowest.
Yeah. So how would you do that?
So that would be like, that's a good question.
It would be 0, 1, and then the rest 0, 0, 1, and then the rest 0. If that second one is this lowest.
Okay. So say that again. 0, 1,
0,
0, 1 for the 6.
negative 1.
negative 1.
Because
Yeah.
we're comparing.
And then the rest.
And then all zeros.
Yeah, so that's an interesting one, and that gets into a little bit about what you might want to do, which is essentially, in general, when you're measuring the responses, you don't really have an idea of where the peak is going to be, but you might have some idea. So, for example, what might you do if you thought that the peak? What would be a good contrast matrix? Let's say you thought the peak was in some range here. So this is 1, 2, 3, 4, 5, 6, 7. So let's say you thought the peak was somewhere in the range of the 5th, 6th, and 7th beta value. What would be a good contrast matrix for seeing whether the peak was significant? You could average the 3, right? So you could have C equals 0, 0, 0, 1, 2, 3, and then all the rest zeros, right? So this is basically, you're trying to characterize the shape of the response. Maybe you care about its peak, or this group had a good idea. You wanted to look at the difference between the peak and the valley. So you could even do something like, let's say you thought the peak was there. You could make -1, -1, -1, 1, 1, 1, somewhere in the middle, and then -1s everywhere else. Okay? So it's really up to you what you want to design, but the idea is the contrast matrix offers you a lot of flexibility in which questions you want to ask. Question? Sorry, I'll get this and then come back to you.
So could you clarify when I would use negative 1 versus 0? Are these interchangeable?
Yeah, so that's a good question. So 0 means you don't care about that point. Okay, so regardless of, and -1 and 1 means you care about the difference between. Yeah, okay. There was a question?
Yeah.
Okay, yeah. So when you zero something out, you're ignoring it.
They don't have to sum to 0 for the contrast.
No, they don't have to sum to 0. Yeah. The only constraint on the contrast matrix is it typically should be full rank. And so let me give you an example of what that means. I'm going to set it up here. So let's say I gave you this contrast matrix, 1, -1, -1, 1. Okay. So sometimes your software might complain about this. So why might your software complain about this contrast matrix? This is for an F statistic, right? It's redundant, yeah, because remember the F statistic doesn't care about the sign. It's a two-sided test. So 1 - 1 or -1, whether A is greater than B or B is greater than A, the F statistic doesn't care. So from the point of view of the F statistic, you don't really have two independent rows. You only have one independent row. Most of the time, the software will be smart enough to say, well, look, that's not a very good contrast matrix, try again. Or I'm just ignoring what you did, and I'm assuming I know better than you. But sometimes it might just fail, in which case you have to fix it. Okay? All right. So let's just recap where we are on the first level analysis. So the first thing is you set up the general linear model, okay, depending on your design. You're going to estimate the beta parameters, okay. You're going to estimate the noise, okay, and then you can define some contrast C, okay, which we just saw some examples of that. And from there, you compute your T or F stats. Okay, so this is what it might look like for a scan. You have your FMRI data, you have your statistical map, and then here you might threshold it depending on show me all the voxels where I had a significance value of 0.05 or 0.01. Okay. So primarily this is really if you're doing a very small study or something, you want to look at the data, or you're doing a pod study, you want to see there's activation. But the real heavy lifting is actually going to occur later, because what we really are going to be setting up is that first level analysis is really just the first step here before it goes into this big group level analysis. Okay, and that's something we'll cover later in the course. Okay, so what we're going to do now is, we're going to do the group analysis later, but today what we're going to do is we're going to switch gears a little bit and now dive a little deeper into this first level analysis in terms of some of the things that we need to consider in setting up our GLM. Okay, so far we've done a very simple GLM. We've only modeled the stimuli. Now we want to talk about what else contributes to the fMRI signal, right? So that gets us to this thing of nuisance terms. Okay, so this is an example where in this plot here, this is time, and what they've done is they've just stacked all the voxels sort of as each column is just the signal values for that point in time. And just sort of, it's a really nice way of looking at the data because it sort of gives you an overall view of what's happening in the data. And so you can sort of see here that, so where it's bright, the signal is getting bright. Where it's dark, the signal is getting dark. And what they've measured here is they've measured respiration, they're measuring heart rate, they're also measuring motion. And you can see, at least in this example, there's very strong correlation. Wherever you see these respiratory effects, you also see it's really affecting the fMRI signal. Okay. This is one where the subject's moving a lot. Okay, so this is sort of a measurement of how much they're moving, and you can sort of see, and they're also, and movement and breathing tend to be very correlated. So you're also seeing them taking deep breaths when they're moving, and so you're seeing these very strong effects in the fMRI signal due to deep breaths, and here probably just mostly due to motion. Okay, but there's a lot of things that can affect your fMRI signal. Motion is one of the big ones, especially in certain populations like kids who tend to move a lot. And a good way of QAing your data is it tends to be most pronounced at the edges of the brain. Okay, so typically if you're looking at an fMRI data set, a good first thing to do is just to click on the edge of the brain and sort of look at the signal there, and that will typically give you motion, because what's happening is any given voxel on the edge of the brain, as the subject moves, the brain is coming in and out of that voxel, right? So the signal change is going to be very big. So this is just showing very bright signal changes at the edges of the brain due to someone, and nodding is very common. Okay. The other thing that a lot of people looked at, and our group has also looked at, is physiological noise. So typically, and it's fairly straightforward now to basically just put the pulse ox on someone's finger and the respiratory belt around their chest. And there are new developments coming out where the newest scanners actually, you don't even need to do that. It just sort of can sense it remotely. Okay, so hopefully we'll have one of those in a few years. But this is an example of, for example, this is the fMRI signal as a function of cardiac cycle. And you can sort of see it's very highly related to cardiac cycle. A number of these slides I've gotten from this human brain mapping talk, so you can sort of see the link there. So this is also showing that those cardiac-related effects tend to really happen. These are maps of sort of where the cardiac effects, the pulsation effects are strongest, and they typically happen around the vessels. Okay, as the vessels are pulsating, that's affecting the brain tissue around it, and so that's going to give rise to cardiac-related effects. Respiration also has a lot of effects, and that is due to the fact that when you breathe, the amount of air in your lungs changes, and that changes the magnetic field all around your body. And that change in the magnetic field can lead to changes in the fMRI signal. Okay. And the interesting thing is all these things are related. So for example, breathing, as we saw, is very related to head movement, and also because of the link between your cardiac activity and your respiratory activity, everything is related. Okay. So even though we're going to talk about them separately, everything is related. Okay. This is an example of looking at not just cardiac pulsations or the actual breathing itself, but the sort of the depth of breathing, the rate of breathing, or your heart rate. And so here what they're looking at is they measure the respiration and the cardiac. So those are, you're seeing, sort of every heartbeat, you're seeing the pulse ox. And then what they do is they basically can come up with a measurement of, how much is the breathing changing, or what is the heart rate at every point in time. And it turns out when you look at that, these are maps showing how correlated the fMRI signal is to either your breathing rate or your heart rate. And you can see there's a lot of correlation there. This is actually showing the percent variance. So in some cases, it's showing that up to 30% of the fMRI signal is explained by heart rate. Okay, and it also varies quite a bit from subject to subject. So in these two subjects, heart rate has a huge effect, and respiration not so much. In this subject, respiration has a huge effect, and heart rate not so much. Okay. So this is going from 2 to 30% variance in the signal. So that's quite a lot in some of these subjects. So one way we can get about that is we can actually look at the signal in areas of the brain that aren't related to, that we don't think should have any neural activity. So for example, in this study, we looked at the magenta thing, voxels are basically where we tried to pick voxels in either the deep white matter or the ventricles. And supposedly there's not a lot of neural activity happening in those areas. And so if we measure those signals, then we should have a fairly good estimate of all these other effects. And it turns out that that's actually true. So on the top here, you're showing, this is a spectrum. So this is frequency, and this is the size of the signal. And in green here, you're sort of seeing the respiratory effects. So 0.2 hertz is breathing about every 5 seconds. Okay, and then here, the cardiac for this subject had about 1.2 second frequency, so a little faster than 60 beats per minute. Okay, and so that's if you actually measured it using the pulse oximeter and the respiratory belt. Now, if you just took the signal from these areas, you actually end up with a very similar spectrum. Okay, so that's why, especially when we talk about resting state fMRI, you'll often hear about people using white matter and CSF regressors. This is why, because if you measure the signals in those areas, they can capture a lot of what's going on. Because sometimes the pulse ox falls off or the person wiggles it off, sometimes the respiratory belt slips down, you don't always get a good signal. So it's nice to have some other ways of measuring these effects. The other thing that you see in fMRI a lot is these low frequency drifts. And this isn't actually even too bad. Sometimes you just see drifts, signals going up or down or up and down. We actually have no idea what causes that. I mean, very little idea. I mean, even after 20, almost 30 years of fMRI, the field just sort of accepts that they're there. Sometimes we know. Sometimes, for example, we know that they're due to heating or something wrong with the system, but oftentimes we just really don't have any idea. They're probably just due to very, very slow effects that we don't really understand. Okay, but they are there, and so typically for most fMRI, we will always model. There will be these what we call a linear trend, which we'll have to model as a nuisance regressor. So then what do you do once you have these nuisance regressors? Well, in here they're basically showing motion regressors. So these are X, Y, and Z translation, and then pitch, roll, and yaw. So these are the 6 motion regressors. And then in this case, they also looked at signal in the white matter and CSF. And so one thing you can do is you can just regress it out. You can just basically say, I'm going to take my data, I'm just going to fit it to a model and regress out everything that can be explained by motion. So for this case, this was a signal before, and then after regressing out motion, it looks, sort of this effect here is largely removed. Okay. This is another example where you can sort of see we're looking at roll and left displacement, and there's a big jump here. And if you look at the fMRI time series, there was also a big in the red, you're seeing the effect on the fMRI time series. In this case, what we did was we used something similar to using white matter and CSF, and we found out what are called the principal components of the noise were. When we regress those out, you go from the red curve to the blue curve, and you sort of see you can take out that effect. Okay? So when things go really well, you can actually take out these effects quite nicely. A very common algorithm you'll probably hear about is something called retro I-core, which has been around since 20 years now, in which case we take the pulse ox and the respiration, do a lot of different signal processing to it, and then regress out those regressors. And you can sort of see, looking at these spectra here, respiration and cardiac are really strong. And then after you apply the algorithm, those peaks are largely removed. All right? And this is a similar thing using respiration depth. So essentially here, this is the respiration signal, and he's using the blue thing as the regressor, sort of the overall envelope of breathing. So this is the fMRI signal before taking out respiration, and here's the fMRI signal after taking it out. Okay, so the idea is that you can take out a lot of these signals. Now the caveat is all these papers are showing like typical voxels, which just means this is where it worked really, really well. Okay, it turns out none of these methods work that well. Okay, they're good enough to publish a paper, but in practice they all have their limitations, and so at the end of the day, you're still going to be left with a lot of nuisance terms in there. Another approach, which is a form of regression, is called temporal filtering. And so this is used, for example, a lot in FSL. Okay? AFNI tends not to do this so much as standard processing, but FSL will always typically try to get you to do some high-pass filtering. Okay? And here, basically, now the nuisance regressors are sort of the low-frequency sinusoids and cosines, is how you can think of it, as regressing out low-frequency terms. And so the idea is, for example, if this is your raw signal, you don't really care about this linear trend. Okay? Unless you have a reason to believe that the brain is actually increasing the signal like that, and in this task there wasn't, it was a block design, then you want to actually take that out of your data. And if you do, that's what's called high-pass filtering, and if you go from here to here. Okay? So now if you try to fit this to your model, you're going to have a much better fit to your model than if you tried to fit that to your model. All right? Now the caveat is you have to pick the cutoff frequency carefully, okay? And essentially what that means is it has to be lower than the frequencies that you care about, okay? And that's going to vary depending on your design. So for example, if you have a design where the brain is changing very slowly, like over tens or hundreds of seconds, then this isn't really going to work, because if you filter that out, then you're getting rid of your effect. But where it does work, it works really well. So for example, this is showing maps before and after temporal filtering, and you're going from very little activation to seeing a lot of activation. Low-pass filtering is, not, I would say, not done quite as much, because usually the high-frequency noise isn't that great, and you don't always have a reason to believe that you should filter it out. And it's more common in resting state fMRI, where maybe we might apply a low-pass filter at 0.1 hertz. But for task-related fMRI, it's you can do it, but it's not necessarily as commonly done. Okay. Okay, and the final caveat is we treat everything as a regressor, right? We treat breathing as a regressor. We treat cardiac pulsations as a regressor. We treat head motion as a nuisance term. Okay, but all of these actually are controlled by the brain, or somehow related to the brain. Okay, so these methods may not really be appropriate, especially if you're looking at something like the autonomic nervous system, or control of breathing, or control of if you're looking at meditation and you're looking at sort of perception of heart rate variability, then you have to be a little bit more careful about what you treat as a regressor, because you could very well be taking out what you care about. Okay, so this isn't a problem that's been solved. It's been a problem that's been pointed out. It turns out things like head motion can be shown to be a trait. Okay, basically, people just, depending on how their brains are wired, just move. Some people are movers and other people are not movers. Okay, and so you want to keep that in mind as you're analyzing your data. Okay, so before we move on to the general linear model, again, are there any questions about nuisance regressors? Okay, yes?
I have a pretty firm appreciation of why one would regress out white matter, but could you give an example of when CSF might be regressed out?
Yeah, well, first of all, CSF is basically just liquid, so there aren't any neurons there. So we would assume that any signal we got in the CSF is just a confound. CSF is going to be sensitive because it's just like water there. It will be sensitive to pulsations due to cardiac. It will be sensitive to breathing effects. It will be sensitive to motion. It's just sensitive to a lot of the signals that are there. Now the caveat to all these methods is that it's often difficult to get a voxel that's purely CSF. So you have matter contamination of it, in which case you're not truly getting this term. Okay. Okay, so let's revisit the general linear model, and so we're going to spend the next section of the talk talking about how to think about this. And so the idea is that we've already looked at the general linear model, and we've sort of related to these hypotheses. So in the null hypothesis, we assume beta equals 0, so that our data should just be equal to basically noise. Okay, and in the alternative hypothesis, beta is not equal to 0, so we expect the data to have a signal term plus a noise term. All right. So now we're going to introduce nuisance regressors, and we want to talk about how that sort of changes what the picture is. So now we're going to split up. This is our X matrix, but for purposes of thinking about nuisance terms, it's useful to break it into two parts: the part of the design matrix that are your regressors of interest, and the part that's your nuisance regressors. And so there will be parameters associated with your signal and parameters associated with your regressors. Okay, so we'll just split that into two. All right, and now we look at our null hypothesis. So now the whole null hypothesis is that just the signal betas are equal to 0. Not all the betas are equal to 0. Okay, and therefore if they're under null hypothesis, my data is actually my nuisance terms plus everything else. Okay. And then in the alternative hypothesis, when the beta s is not equal to 0, then it's my signal plus my nuisance terms plus everything else. Okay. So if these nuisance terms can explain a lot of my data, then there's actually no reason for me to reject the null hypothesis. Okay, and that's going to be a very important point. If some nuisance, if something you think is totally unrelated to your explain most of your data, then there's very little for your data for your model to explain. Okay. So this is just sort of a partitioning of the X matrix, which is here. Okay. So even though it's useful to think about this, it's much more standard to just keep this original notation and then just pick our contrast matrix such that it only picks up these beta s's, right? So we're going to pick out contrast matrix, for example, where C times the overall beta is just equal to my my signal betas. All right. So in this case, the null hypothesis is C beta equals 0. Okay, which is the same as saying all my beta s's equals 0, which gives me the same signal. Okay, once again, the data is the nuisance plus everything else. And then when C beta is not equal to 0, then my signal part comes in. Okay, so that's essentially what we're doing. We're going to use our contrast matrices now, not only to look at signal contrast, but also to tell our software what's signal and what's nuisance. And it's very simple. Anything that's nuisance, you just assign a 0 to. Basically, you say, I don't care about it. Okay, but you still have to include it in your model because if it can explain your data, it's going to affect your statistics. So this is an example that we looked at last time where we had 4 columns of signal regressors and I believe 7 columns of nuisance regressors. Okay? So if you look at this contrast matrix, you see the first 4 columns have 1s in them. Everything else is just zeros. All right? And so when you're looking at contrast matrices, this is also, this is something, and sometimes the software will just do that for you, but if not, you have to put that in. Okay? Okay, so let's look at the GLM with confounds. So for example, in this case, I have my stimulus, I've convolved it with an HRF. So this is, and this is some older slides, but these are essentially, this is like the design matrix I care about. This is the part that is my nuisance regressors. Okay, and in this case, I have a term of all 1s, and then this term is a linear trend. Okay, it just goes from 1 to 9. So we've talked a little bit about why we have a linear trend because the data tend to have this linear trend. Why do we also have this column of 1s as a nuisance confound? Any idea?
Anything constant?
Yeah.
Probably not related.
Right. So the idea is that when we measure the fMRI signal, we have a picture of the brain, right? And then we just repeat that over and over again. So if we just had a constant picture of the brain, we assume that there's no activation. So what we really care about is the fluctuations of the brain. And it turns out this fMRI, that mean signal really has no meaning to it. Okay. So when we talk about bold, we're always talking about percent fluctuations. And so we're looking at percent fluctuations. We could either take the mean out beforehand, or we can just put it in the GLM and let the GLM handle it. Okay. And in general, if the GLM can do it, let the GLM do it, because then it'll always be right. If you try to do it yourself, you have to be a little careful. Okay? So even though the GLM is a little more scary at the beginning, over time it can be your best friend because you're basically stating all the assumptions about everything, and then the math will be done correctly. Okay? So basically we have the mean as a confound, because we're looking at percent change in bold. Okay? Oops. Okay, so this is just showing what that looks like. So in this case, we have a linear trend. we have a constant term, we have our noise term, and then we have our stimulus here. And we add all those things up together, and that gives us our measured signal. All right? So let me just talk a little bit about something called Legendre polynomials. All you need to know is AFNI loves to use these. Okay, so in AFNI, if you ever see the term pol-ort, that stands for polynomial orthogonal. Okay, and so these are what AFNI uses to model confounds. So this is your constant term. This is a linear trend. So this would be order 0, order 1, and this quadratic is order 2. Okay, so AFNI will always do the 0th and first order for you. Okay, unless you tell it otherwise. So it's always going to put in a constant and linear trend for you. Now, whether you want to go up higher in terms of a quadratic term or a cubic term, it's a little more controversial whether you should add these terms. I think sometimes, I mean, I'm sort of comfortable with a quadratic term. I'm less comfortable with maybe the cubic term or the quintic terms, things like that, because you don't necessarily see that too much in FMRI data. But AFNI will let you decide, or it will try to decide for you. Okay? So if you see pol-ort, it's because it's trying to model these low frequency confounds for you and take them out of your data. All right? This, I guess, I forgot this had animation. This is just reminding us that in this case, you know, this in our notation, this would be our x sub s, and these two things would be combined to be our nuisance terms. Okay, so in general, we have our design matrix. We're going to have some nuisance terms that are just very vanilla, that are not measured. They're just things that we know should exist, like the constant term and the trend. And then we're going to have another set of nuisance terms. Oh, the guy's even breathing and the heart's beating. Okay, cool. This is something one of my grad students made up a long time ago. And then you're going to have another set of nuisance terms that are actually measured. Okay, either using external monitoring or from the data itself. Okay, so there's sort of two categories of nuisance terms. And then you put all those into a general linear model. So for example, in this case, this is the x of s component, and then here are the nuisance terms there. All right. AFNI will display it this way, and I'm not sure why they're organizing it this way, but here is the x of s term, and then this is all the head motion, and this is all the baseline and drift terms, and both of these combine to give you your x of n term, your nuisance terms. And AFNI sort of, it's a little tricky, but this is actually, if you look at this, let's go through this because you often see things like this. From looking at these nuisance terms here, I can tell that this is 3 runs concatenated together. Okay, because basically they're saying black is bigger numbers and white is smaller numbers, and each column of x is scaled separately. And so this can be a little confusing when you're using AFNI, but essentially you sort of see this is a constant term, this constant term, that's another constant term. So each run has its own constant term. Okay, because the mean value of any one run in FMRI is meaningless. Okay, behind the scenes there's all these numbers and scaling factors, so it may just be that in one run your signal is 10% higher because the system just changed something for you. Okay, so that's why the mean is sort of a confound. And then for each of these you also have a linear trend. Okay, so I can tell that there's 3 runs done there, each where he's modeling a constant and a linear trend for that run. Okay, and he's doing that separately because different runs may have different linear trends and different constants in them. Okay? So when we get to group analysis, there's going to be a question of when you have multiple runs, what's the right way to analyze it? Do you concatenate them? Do you do each one separately? And hopefully we'll get into that later. Okay, but for now, I just want to point out you that's looking at the matrix, you can tell what's going on. Okay, so let's talk a little bit about the effects, what happens when you include nuisance regressors in your GLM. So remember, a t-statistic has this form. It's your parameter estimate, C beta hat, divided by a standard deviation. And then it had this form here, and what we really care about for now is this term here, the x, the sigma hat, because we don't really have regression isn't going to affect this because that's determined by your design. Okay. So in general, for a t-stat, we want to make we like big t-stats, right? Because then we can publish our paper, we can finish our thesis. Small t-stats, not so happy, right? Okay. So the goal is, can I make the residual smaller, right? Can I? And the way to do that is by having a better model of my data. Okay. So my data has part of it that can be explained by the nuisance regressors, then that's going to reduce my sigma hat, right? If I don't have those nuisance regressors in there, my model can't explain what's going on in the data, so it's going to assign all of that to the residuals and make that sigma hat bigger. But if I can model those nuisance terms, I can make that sigma hat smaller. I can make my t-stat go up. So this is an example of that. So so this is the data. Looks really noisy. Okay, and then after the data, after we've removed the terms here, these are two different methods of doing that. You can sort of see we have a much better fit to the model, right? So in this case, the sigma hat would have gone down quite a bit. Okay, because if you can think about the residuals here, this has a very large. It's going to have a very large residual standard deviation. Okay, so in this case, you're going to have much better ability to detect your activation. And that's shown here where we're looking at if you do no correction and you go different types of correction. This is the number of activated voxels that we found in this study, and the good news was that in this case you almost double the number of activated voxels you found. Okay. So that's one reason to do this, is basically when things go really well, these things really help your t-stats. Okay. This is another example here where now this is slightly different. Now this is basically a case where if I don't include the regressors in my general linear model, I got a lot of spurious activity. Okay, and this is a case what we'll get into where now we're dealing with what happens if your nuisance regressors are correlated with your stimulus. Okay. So now we're running into a different issue, which is basically, so for example, if you have a paradigm where every time the person sees the picture, they nod their head, then you're going to have a stimulus-correlated regressor. Okay? And so they're nodding their head, so that's causing all these signal changes, which are not necessarily related to what they're doing with the part of the brain they care about. Obviously, they're using some part of their brain, okay, but that may not be the part of the brain you care about. Okay? So the idea is by including those regressors in, we can clean up our activation map by just assigning voxels that were more related to what we cared about, our stimulus. Okay. So to do that, we're going to give you a slightly geometric view of that, just a few slides to convince you what's going on, and then we'll look at some examples. So this is the data that we've measured. And basically now what we're saying is our data can be explained by either our signal regressors or our nuisance regressors. Okay, so the combined model space has both my signal and my nuisance regressor. So anything in that plane can be explained. Okay, and so what can be explained is this part here. That's what can be explained by both my models. Okay, but the statistics only cares about that part that can be explained by, so this is saying that this much of my data can be explained by, or sorry, this graph, this arrow here and this arrow here combine to add up to this overall arrow. So this is the amount of data that can be explained by my signal, and this is the amount of data that can be explained by my nuisance regressor. But it turns out that when I do the statistic, I'm only allowed to look at the amount of data that cannot be explained, that can only be explained by my model and cannot be explained by my nuisance regressor. Okay? And so you can sort of see as those two things become more and more similar, there's going to be less and less stuff for my model to explain. Okay? So if my stimulus and my nuisance regressor are very correlated, then it's really going to hurt my statistics. Okay. So this is just sort of setting it up from the one of the FSL readings. Here I have my stimulus, here I have my motion regressor, and you can sort of see here this is a stimulus-related regressor in the sense that the motion is occurring at the peaks of the stimulus. So if I were to model my data, like let's say there was some combination of stimulus plus motion, I might get that as what the data looks like without noise, and this is what the data looks like with noise. And then when I try to fit both of these. I'm going to try to fit this and this to this data. Then I'm going to get an estimate of beta 1 and beta 2. Okay, so the model is basically looking for the combinations of beta 1 and beta 2 that when we sum up, the weighted regressors are going to explain my data. Okay, so now when you do the general model, it's going to just find whatever combination best explains your data. Okay, so so it turns out then that the F statistic is really then just this. It's now going to be, this is the part of the data that can be explained only by my model, and then this you can divide it by the error. Okay, and so the thing is if this term gets really small, okay, as this term gets really small, your F stat's going to go down, and that term is going to get small if the signal and the nuisance regressors are too similar, right? And then just geometrically what it means is the F-stat is just this length here. This is what can be explained only by the model, sort of divided by this length here. Okay, and so that's that cotangent squared theta that we saw before. But now it's basically, now we're in a weird place where it's everything that can't be explained by the nuisance regressors. And then our correlation coefficient is just this part. This is the part of the data that can't be explained by my nuisance regressors, and we're looking at the part that can only be explained by my model. And so that's that cosine squared theta. So all this sort of geometry still applies. The main thing is to realize that, and the thing we're going to show some examples of, is basically you have to see everything is what's left over after the nuisance regressors have had the first shot. Okay, so it's almost like you have to, the nuisance regressors get first dibs on the data. Okay, they go in and they look at the data and say, I can explain all of this in my data. And what you're left with is everything else. Okay, so if the nuisance regressors can explain all your data, then you don't really have anything left to explain. So let's take a look at an example of that. I'm going to skip this for now, but let's just go to this example here. So this is what we have here. We have our stimulus and our motion. And now in this case, when we add up, so what we're saying is that the right way to do it is basically, this is my model, sort of minus the part that can be explained by the nuisance. Okay, so this model function here, this new model function, is basically what's called orthogonal to my motion. There's no part of this new model function that's explained by my motion. Okay, and then this is my measured data, and basically what I have to do is I have to first take out any part of the data that can be explained by my motion. Okay, and so that leaves me with this black curve here. Okay, so at the end of the day, I'd say how much of my data here in black can be explained by my model after I've taken out the nuisance terms. Okay, so you have to take out the nuisance effects from both the data and also from the model, and then you do everything on that leftover space. Okay, and so in this case, we're finding that so here you're showing the data in black being fit by the model in red there. Okay, so now let's take a more severe case where now the stimulus and the motion are more correlated. So this is something where now if I look at, for example, this is my data before I take out my motion, and this is the data after. Okay, and you can sort of see, because the motion can explain a lot of that up-down behavior, I'm not really left over with very much. Now I also have to take the motion out of my regressor, and so what I'm left with is that. Okay. this example, there's still a fairly good fit, but in general, you're not going to have as good of a fit. And so you will find that there are cases where if your stimulus and your confounds are too correlated, that's going to give you a problem in your detection. So we're going to wind up for the last 10 minutes just sort of, not going to have too much time to go into design, so I'm just going to sort of give you some of the highlights and some of the some intuition behind different experimental designs. But let's start off with this one here. So this might be, for example, where I had a stimulus that went off and on like that, okay? And it led to some response. And I also, let's say I have a linear trend confound here, and then also here I have a quadratic trend. Okay, so the signal is going low, it's getting high, it's going low again, all right? So let's say this is what I measured. Okay, I measure that, okay? And the problem is that this looks a lot, somewhat like that, okay? So if the similarity between those two means that this is really not going to be very good. My ability to detect whether anything went on is going to be what's left over after I take out this variation here, okay? So that's why we tend not to do these very low frequency designs. So this would be called like a one block design because they're too similar to these drifts that can happen. Okay, so if I have a 5-minute long scan and I only have one like 2-minute block in the middle, then it's gonna, anything that goes up and down very slowly is gonna look too much like my brain response. So then when I regress all that out first, I'm really gonna hurt my statistics. And when I add noise, it becomes even more thing. So for example, if I add noise, now that one block, that block, and the nuisance term start looking even more similar. Okay, so that's why typically you're going to see block designs are going to have blocks of 30 seconds or less. So it's going to be like 30 seconds on, 30 seconds off, because now you can sort of see these blocks here are much different than this nuisance term. Okay, so when I take out the effect of the nuisance term, I'm not going to really affect this activity as much. Okay. And then finally, we're going to just say very little about experimental design, which is experimental design is basically, let's say you have 3 conditions. The question is, how do you want to present those conditions? In what order do you want to present those conditions? And why do you worry about design? Well, because scans are expensive, subjects are difficult to find, fMRI data are noisy. So if you design your experiment badly, you can really shoot yourself in the foot. Okay. I love this quote by Ernest Rutherford: "If your result needs a statistician, then you should design a better experiment." Okay, that's not really true, but it is true in the sense that if you really can't see the result by eye, and you really need lots of statistics to do it, then especially for fMRI, it's a little, you have to be a little bit worried. Okay. Now, obviously, now with these big, huge studies, we can just detect very small effect sizes, but whether they're really meaningful or not is a question. Okay. Okay. So let's actually we'll just do this the old-fashioned way. So there are 5 designs here. Okay. So I want you to look at them, and so each of these is a different stimulus pattern. Okay. And what I've shown is the bold response to each of the stimulus patterns. Okay. So just think about this for a minute, and we're just going to take a rough poll. So I'm going to be asking you who thinks A, B, C, D, or E is the best design. Okay. All right. So who thinks A is a good design? Anybody? Okay. B. Okay. So a few votes for B. Whoops. Oops. Okay. How about C? Some votes for C. Okay, D. Okay. And E? Okay, good. All right, so they're all very good designs. Okay, it's just, so the bottom line is any is okay, and it just depends on what question you're asking. So, so I'm just going to give you my 5-minute spiel on what we care about. One is statistical efficiency. We want to maximize the contrast of interest versus the noise. And the other thing is psychological factors. Is the design too boring? If the subject falls asleep, you know, your fMRI signal is not going to be very good. All Okay, so remember our t-stat is our estimate over its standard deviation, and efficiency is really looking at this. How do we reduce the variance of our parameter estimate? And it turns out that depends on my X matrix. Okay, so that's where we have some control over our what we're looking at. But it turns out that the best design depends on the question you're asking. So, for example, you might ask, where is the activation? So we assume we know the shape, but we don't know its amplitude. Or sometimes we know something about the shape. Okay? On the other hand, you may already know where you expect the activation. For example, you're doing memory encoding, you know you're interested in the effect in the hippocampus. So you're willing to just say, I'm just going to look at the hippocampus. I don't need to look for the hippocampus using fMRI. I know where it is. And so I'm just going to focus in on the hippocampus. And what I really care about is the shape of the response. I want to see how quickly it goes up and how quickly it goes down. And does that change with my experiment? And so therefore, we want to know something about the shape. And we don't necessarily care about where it is. Okay. Turns out those are fundamentally different questions. Okay. Because the beta estimates, the betas that you're trying to estimate are different, and it's going to give you different answers for what's the best design. So I'm just going to give you an image-based example, and then I'll tell you the answer. And I think we can actually do this in a short amount of time. So here is, there's an image of something in there. Okay, there's actually a media image there. Can anyone see it? Or there may be multiple images of something in there. Can anyone see that? Okay, so not very good detection power here, right? Really can't see what's going on here. How about here? Is there something there? Okay, good. So you sort of see that there might be something there. Okay. How about here? Is there something there? Okay, great. So now the question is, that something that's there is one image that's repeated over and over again. So what image have I repeated over and over again here? It's just overlapping itself. Okay. Can anyone tell what image that is? If you know the answer, don't say, because some people might know the answer. Okay. So this is a really great design if I just want to see if something's there, right? But it's not really a good design if I want to tell, what the shape. So the image is like the shape. There's some shape there that's being repeated over and over again. It just turns out it's an image of somebody. Okay. The noise level here. Now, can you tell if there's something there? Periodically, right? See there, it's there, it's there. Right? It's, I guess, there, right? Okay. So there's something there. Can you tell what it might be? A face. Okay. All right. Whose face? Abe Lincoln. Close. Actually, quite close. Okay. Now, is it Abe? Okay. Any guesses? Okay. Now can you tell? Does that help at all? No. So this doesn't really help determine the face, but this is actually getting a little closer, right? This sort of confirms that it probably is a face, but we don't really know whose face it is. Okay, now I'm lowering the nose level more. So it's not Abe, but it's another, dare I say, great president. And that makes it that's really easy to see there, and this not so much. Okay, so the idea is this is like an event-related design. Okay, and this is a block design. Okay, so that's really all you need to know. That basically, if I really want to know where something is, I want to use a block design. If I really want to characterize the shape of the impulse function, in this case looking at who it is, I want to use event-related design. Okay, and so that's the fundamental trade-off, that what you'll see in the literature, that if you're, for example, if you're just starting off a new project, and if you can do a block design, because you have no idea what areas of the brain you care about, then the block design is going to be the best for finding out where did it happen. Okay? But if you already know what areas of the brain you really care about, and you want to do some more sophisticated analyses, then you might want to go to an event-related design. And it turns out that there's this trade-off, and so you can actually pick designs all along that curve that trade off these two aspects, and that's those middle designs that you saw that traded those off. Okay. So let me just, let's see, I'm going to skip over most of this. So the only other thing is that that's a statistical thing. What we also care about, as we talked about, is problems with habituation, anticipation, and boredom. Okay? And so that leads to favoring random designs over sort of block designs. Okay? So that's another factor that you might want to consider. And then let's see. The last thing I want to talk about is oftentimes there's designs where you actually can't decide. You don't have free reign over the order of the stimuli. For example, if you have a probe, distractor, and a decision, those always have to go in that order. And so the timing of those, it's not like you can order them any way you want. Whereas other designs, you can have the order any way you want. You could have A, B, C, C, B, A. But there might be designs that have design constraints. Okay? So the area of design is, we understand this basic trade-off between estimating the shape and sort of just getting an activation. But for these more complicated designs, there's really no good theory yet for doing that. There is a lot of software available. For example, there's these genetic algorithms that you can use. And I've listed here in the notes some software packages you can use. But in general, it's still an area that we don't really have a good idea of how to do it once you move away from sort of these very basic designs. Okay, so I think that's good for today. So there's no class on Monday. It's MLK holiday. And then starting on Wednesday, there'll be a new set of lectures to do the next part of the course. Okay, all right, thanks.